ja was übersprungen. So. We can start for the second part of the day. Okay. This I already told you on the paper. This was also on the print out presentation. We compare what is a geometric mean radius. The geometric mean radius is the mean value we calculated for a point against a line, and if we have two areas, we have to do this integral. Because it's important, I will put it on the flip chart. So, in the next time we will discuss this here. This we don't calculate, because this is given and it's too complicated to calculate. Then we have to make a fourth dimensional integral. I already told that a full copper plate, the G is the upper, G is that. So, if you have a tube, it's also the distance of the center. If you have a full, it's not shown here, to a tube, it's also the distance of the center. Always G is up this distance A. Okay. For strapline conductors, we have a chapter 3 for copper plated and for copper boxes of transformer. So, what to do if we have such a way? We can discuss this. We have to do an integral. We have here 1, 2, A, B, C, D, E, and F. What we have to do? It's the same if we have copper plated. If we have copper plated, such in this way, we have here A, B, C, D, E, and F. We have to calculate C to E. And all the others. And we have to combine this now. But now the theory, how to combine all, we have here G, A, E, G, A, F, 1, G, B, C, and D, B, C, and D, and then we have E, and E, and F. And we have to, first, we have to calculate all the 8 values. And then we are looking for a formula which we can use to, if we call this 1 and this 2, what is G1, 2? Geometric mean radius between one copper plated electrode and another copper plated electrode. But first we have to do some theory, and this theory is in reaccuracy. That is, if you want to calculate a reactance of the ERF, you have to use this formula. So, first, we will have I put it away, it's not good. A, B, C, D, E, and M. We have to do following. We have here an area A, B, AC, AD. Each conductor has an area. It may be different, it may be the same. If the same area, it's easier. It's less work. But first, I want to interpret this one. So, we have to say ln G, and now I say 1 to 2. 1 to 2. What is it? ln 1 to 2. You have to look at this formula. What we have to do? We have to do 1 and 2. A1 times A2. A1 is AA, AB, AC, AD. A2 is area B, area F. So that I have to input. And then we have to do the sum. We have to look for all radians. So I think this is the link. Mr. Tim?
Yeah.
Can you put it to the flip chart?
Yeah.
It's not here. It's not here. We have. It's not good for what I do today. I think I can do it better if you understand it. Sorry for that. We have to say LNG according to this. And then we have to do the sum. We have to do the sum about all values. AA, ln GAE. This one, no? And then the same for B. So G. The same for C. AC. And yeah, D. D
F E.
D and E.
D and E.
Then and the next one. Next one. You have to change F, E and F here.
Yeah, yeah.
And then A,
Yeah, so same.
Okay.
Yeah.
Okay. It's a long way.
Yeah.
Yes.
If you make it in a loop in a program, it's not so much problem. What to do if all these areas the same? If AA, AC, AB, AD, AA is AD, is AC, is AD, and E area F. E is area F. Then it becomes much easier. Then it becomes much easier, and all the factors here, all the factors are the same. All the factors are the same, and then we will get LNG, and if then this then all the factors in sum are the whole factor A1, AD, and A2 is AE. You can this formula, or you can use a simple formula. Then you have is ln GA. It's too long. I need ln GA. I have all from A and B. And then we have ln to add ln GC. CE was ln CF. ln CE is here. CF. ln CF. V is C.
Yep. C, yep.
D.
D, E, D, yep.
D. So, and then we have to put this factor before, and this is 1/6. 1/8. 1/8. Because all values are the same, then we have can say we have 1/8. We have this, or we can G is 8. And so on. If you have 8 geometric mean radiuses with the same area, you have to build the 8 root of this. If you have 16, you have to do the 16th. So either this or this. That's the same. And this is this formula, and these are these two formulas. And this here is the application to two conductors, to conductors. This is conductor 1 and 2, and this have A, B, C, D. This comes from this. Normally, in a real construction, we don't have the different areas, I think. So this is the important. These are the important formulas. You can first. I explained this.
Yeah.
This is this one.
Yeah.
If you come to this formula, if you have this formula in over there, and you make from the integral a sum, and then you get this one. So, what's now on? Result, geometric mean values of one conductor by itself. Why now by itself? Geometric mean radius by itself. It's possible that now, until now, we have discussed two conductors, one conductor again one conductor. One conductor again another conductor is mutual reactance.
Yeah.
And if we now make limits that we say we want to calculate the geometric mean radius of this conductor of itself, then we will get self-inductance. And we have to calculate the geometric mean radius of the conductor of itself. So, and if you make this, you will get this result for a full conductor. For if there is no current displacement, you will get this. Is a geometric mean radius of a full conductor, full round conductor is the radius, and this radius has to multiply by this expression, the power of 0.25 of the E function. Or if you build the logarithmus, the log, then you will get this. So, that's a full conductor. That's only a sign. I don't demonstrate here how to calculate. I think I have to do this amount of hours, 2 hours, I will do it, but it's a lot of work to do this. Because you have to integrate about 4 dimensions. No? So, and if you do it for a cube, which are very small, you will get that the geometric mean radius is the radius of the cube. So, the next one is, this I know by my head, this one and this one. This one I have to look in the list of formulas. I don't know. I have I have programmed it several times, not only in your program, also in the calculation. If I make the script, I have a program as a subprogram. It's not easy to explain why it is so and so. You have to put in the values, and then you will get the geometric mean radius is almost between this radius. Okay. So the next one. Okay. So, if you have one conductor with 1 and 2, well, what to do now? What to do now? You have G11, G22. What do we have also? G21 and G12. But these are equal. So, but we have to do, yeah, it's easier to think we have 1 and 1 and 1 and 2. Up to the 1 and 2 and 1 and 2. That's the same conductor, but for understanding, it's better. We have that to that, to that, to that, to that, to that. We have 4. This 4, and of this 4, we have to calculate one value. 4 values. It's one possibility. When this is conductor A, GAA is. So we have to combine all this. G11, G22, G21, G12. We have to multiply. And if the areas are the same, then we have to do okay. We have GAA. Because normally you calculate not G, because log sheet you calculate. So, and if this is a distance A, you put A for this, and for this, and then you can say GAA. And GAA. LN. Where I get this one, if the area is the same and the form is the same, G11 is G22, and this is the same, this is the same, and then you can here say that is for this situation.
Sind Sie da rechts oben?
Ich bin da rechts oben, ja.
Und wie ist es bei einer 3? This is to reduce, if you have a 2-wire system, to reduce it to 1 cable, 2-cable system. Und wie sieht das aus bei 3?
Auf 3.
Ah ja.
This was were 2 conductors. Mr. Tim asked for 3. We can give the answer. The answer is here. So, and if you have this one, it's always better to tell. They are on the same position, while it's safe mutual reactance. It's von itself. 1, 2, 3, 4, 5. So can we forget it? 6. And normally the areas are the same.
Yeah.
And if the areas are the same, we can do. We have now 9 of this conductor, and then we have to say when this is 1, conductor 1, to conductor 1, we have G11 is 9 root of G Now we have all 8. Now come these BA, B, G, C, now come C, C. So now we have to look what the same. GAA, GBB, and GCC, because they have the same form. So, we will notice. Three.
Yeah.
So, AB and AB and BA are the same.
Yeah.
G, AB.
Okay.
So, AC, CA is the same. C and CB is the same. So now we have 3 conductors. That's the formula, which is there.
Und wenn die 3 sich in einem Dreieck befinden,
Mr. Tim has another exercise for us.
well, it is important, wenn wir ein 3-Leiter-System haben.
3 conductors.
And all equal is distance.
B, C. We have here the distance B, A. We have here the distance A, and here the distance A. And now we have to put in here G11. This reminds GAA. GAB, AB, there is A, 6. G11 is the third of GAA.
Dritte Wurzel bitte. Ah ja. Und jetzt wie ist das beim... kann man das benutzen, wenn man 3 Seile hat?
Wenn die trianguliert, auch wenn die...
ja, jetzt kommt 4 Seile bitte.
Mr. Tim asked for the next one. Exercise. We will do that.
We have a system with 4 cables.
4
With the same distance. Yeah?
cables or tubes in the transformer line. It's the same. A, B, C und D. Quadratisch oder rechteckig?
Quadratisch.
Quadratisch. A. Ja. Ja. So, we have GAA to calculate. All the same. What am I going to do now? We have, it's possible to say fourth root of GAA times GAB times GAC and GAD. Because if you have only for this special case, because from A to all 3 others is the same as from C to all 3 others and from D to all 3 others.
True.
And you can put in here for GAA, you have to calculate, otherwise then you have AB and AB. I will make here B. That's easier. That's not easier. But if you have a flexible cable, it's not always the same. Then you AB you have to. AB is A. AC is B. And here you have square root of. Oh, that's the diagram. Okay, that means you can calculate this geometric mean radius.
Was haben Sie da raus? 4. Wurzel aus?
Ich habe jetzt das mal abgewandelt mit der Breite A und B.
Ach so.
Und
Hier kommt jetzt 4. Wurzel, nicht?
Ja, 4. Wurzel aus GAA mal A mal B mal Wurzel aus A Quadrat plus B Quadrat.
Ich habe GAB Quadrat mal GAD. Ist das dasselbe?
Habe ich nicht mitgekriegt. Was haben Sie gesagt?
Ich habe GAA, 4. Wurzel aus GAA.
GAA.
Mal GAB Quadrat.
B Quadrat, ja.
Mal GAD.
Ist das gleiche.
Ja, jetzt habe ich noch. Now we will ask what is the reason why we are doing this. Look at this. Yeah? You know what this is? Transformer connection. Yeah? Transformer connection with 8 bus bars in each phase. You can also use this with this formula if you have this. Yeah? It's a little bit longer. You understand, yeah? Why we are making this.
Is this one phase or is it 3 phase?
3 phase. This is a triangle system, yes? 1, 2, 3 phases. But if you want to calculate these self-reactants and mutual reactants, we need this formula of Ahlers. Yeah, is this correct? You understand?
Yes.
You should say yes, and you should say yes. No. You know? This is star connection, not a delta connection. It was this is star connection of a transformer, 60 MVA. Okay? You can also use this formula for calculate the reactance of the system, because the first steps, if you connect your system, alkaline system, you use the same distance. Perhaps you use put this together to a rectangular system. I don't think so. You will also connect here flexible cables, little flexible cables, because if this is moving and you need some distance of the system, this is a typical system, water cooled. The water cooling is going into the transformer. These are always tubes for cooling water. Okay, ist das ein Beispiel, wo man sowas auch weiter benutzen kann?
Kann man schon mal reden, das sind 4 Leiter, ne? Nee.
Nein, es sind 8.
8?
Yeah.
8 conductors.
Yeah, this is very. But this is same. Also Sie sind immer noch bei der Selbstinduktivität, nicht?
Ja.
Self-inductance.
Ja, da sind wir heute Nachmittag erstmal angefangen.
Ja.
Self-inductance.
Self-inductance. Ja.
So, if you have here A and here A. Oh. You have, we have 1, 2, 3, 4, 5, 6, 7, 8. We have to do 8. We have coupling of this one from this to A. We will begin with AA.
AB,
AB, AC.
Yes.
So 2. 2A. That's 2F. And 3A. So,
you see, I've shown this example that you are able now to calculate the self-inductance of every connection. Is that clear? Of every connection you have. It must be not easy. We have in our program only 4 cables, for example. But you can also connect this to with 8 conductors in each phase.
If you have 8 conductors, you can put in, for example, the last example was this one. If you have this, and you can put in only this one. If you calculate this EMR of this, then put in, and you will get the result is 40 millimeters. G is 40 millimeter. We put in one cylinder with 40 millimeters.
This is the same. This is the same for cable, for flexible cables. You see here in these flexible cables, you have 6 tubes in this picture. The other tubes are water cooled.
Yeah.
And you can also calculate this. This is a cylindrical system. Yeah, and this is the reason which was the company told you, GMR. Yeah? Okay? So, every kind of high current system, we are now able to calculate the self-reactance. This is the first step.
The self and the mutual reactance we quite discussed before.
Yeah. And the mutual between different phases, we calculate later. Okay? Ich hoffe nicht, dass Sie was dagegen haben, wenn ich was dazu
Nein, gerne,
sage.
gerne. Dann
Ja.
habe ich ein bisschen Pause gelassen. Mr. Tim asked if I have something against that detail. It's good. He put some examples, practical examples, and that's very good. We learn something. So,
You wanted Mr. Young wanted that you learn theory. The theory which is behind our program.
Yeah.
Yeah, therefore he said we want 3 days of theory and 2 days of practical application with the program.
Yeah.
This is the reason, and that we are doing now.
Yeah.
It's not easy to understand. Yeah?
so
But you can find this book never in the world. This book is only written for you. That's it. Okay?
So, I think this is not practical. If you have a big conductor and a small conductor, if you have 2 tubes, 3 tubes, 4 tubes, you never would make one different as the other. It makes no sense.
Why? What is the reason? Because if you make parallel A and B, A would have more current than B.
Yeah.
There would be more current flowing, current density would be higher. Therefore, you will choose only conductors with the same surface.
But,
Yeah.
but you, if you use this formula as sum, you can make this and calculate this. But I think it makes no sense. I will explain here because it's not practical. Okay. Now we start first. We start the example. All the things we have had, we will get now used for calculation of this. So, we have already calculated this with another method. If we go to chapter 1, where's my chapter 1? This. Motion. Here you see. Now we have had here a result. This result was this. So, and x is 2p times f. 2 0 L F That will be the result with this method. Now we say we will use all the things we have just heard. What do we have? We have A and B. We have, and this is the loop 1. x11 is 1. This above is the result. This result we will look to calculate. What's x11? What do we have to calculate? What can we calculate here? On this. Let's sort out. So, remember this exercise. Now we have this. We have one loop with only 2 conductors. What can we calculate? What can we calculate? Mutual reactances, self-reactances. To calculate. We have 2 conductors, A and B. Which reactants can we calculate if we have 2 conductors? How many possibilities are there with the conductors?
First we calculate self and mutual reactance.
We calculate XAA, XBB is self reactance, and XAB is XBA. AB is XBA. Is mutual reactance. Consider the conductors. We want to know the self-reactance of the loop 1, and then we have to calculate with this formulas, and then we have to make the whole reactance. How is it to be calculated? XAA XBB minus, is it correct?
XAB minus XB.
And that's the same?
Yes.
This is, and because conductor A is conductor B, GAA is GAB, BB, we have XAA is XBB, should be an X. So then we can take X11 is 2 times it's XAA minus XAB. So now we have to look. Now we have to calculate XAA and XAB. Where we get this from? We have to look at the formulas which we can use. What formula can we use? We look at the problem here. The problem is that we have two conductors against two conductors. That to reactance calculation, we have A and B. We have this. That means we have to calculate GAB. What is GAB? We have here A, and yeah, that's easy. GAB is A. So, what we have a radius of 3 millimeters. Do we have at 3 millimeters current suppression?
No.
Density suppression? No. Current suppression begins at 9 millimeters, we say. So we have to look what is GAB, AA. GAA. We have to look into the formula. The formula. My wife has another mouse. It works maybe better. I want, yeah. So, which case we have now of this many formulas? Yes. We have outside radius. It's called here R. So we have to look to the problem now. Where's the problem? We have to solve. It's the problem we have to solve. So we have XAA and XAB to calculate. And now we have to look for a formula for XAA. XAA. So, no. It's easier for you in the paper, but I have to look here from 1 to 1, where we have the formula for X. This one. So, now we have here 3 formulas. Which one we will use? We have to discuss. Sorry.
Also Naturübung.
Yeah, first I have to drink it. Sorry.
Here's also not used, very much used. What is it, your?
Yeah.
Yes?
Yeah.
Okay, you want to have?
So we have 2 parallels, and we have this case here. Then this is much work, this is less work, and this is much less work. And it's extremely less work. And if we can use this, it's better than this. The difference between both in values we will discuss later. And I think it's enough to have this here. Because the length is very big compared to the G. That means I will use this formula. So, XAA. Here's 1, 2. Always change 1 and 2 and A and B. It's mu0 times F times L ln 2L to G GAA.
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 Yeah.
I will write GAA. GAA. And then
minus 1.
-1. Then I will write the same for GBB. And then 2L. GA. No, that's the same. That's not good for me. Okay, AB. What's GAB? Which value? Is A. But I will write here GAB, -1, but I have done here GAA. So, now I will input these two values. GAB, A, -1. So, now I will input here. I have plus and minus. And then 2L. And this one goes away.
Yes.
And then minus ln
2L.
So I take this ln in one ln. So minus ln means
Yes.
okay. We can it goes away, and we have x11 is times ln R to R, and then minus ln that. I put this together, and ln A and if you divide ln A minus A. Okay, and now we get the result. Times ln A to R, and this is 1/4. Let's say inverse function. We get minus 1. And this is with this method, we get the same value as the method before. This method does not show what is inner reactance and what is outside reactance, but it gives the same value. So that means this method we developed with these formulas, and always for this G we have to put in the geometric mean value. If we have mutual reactance, we have to put in the geometric mean values between two conductors, and with self reactance we have to put the geometric mean value of the conductor of itself.
Well, I think this is a very important step of today, that you are now able to calculate the reactance of simple long reactors, loops. We also calculate the loop, not of single parts. We calculate the loop, from 1 to 2. This is a very important step for you. You can, if you have a high CAN system and you want to go into the program, you can calculate this by this formula. This is very important.
So we use the right one. And now we have to go back to the example where we are. We are at this example. We did calculate this. So, and here is only, I told my wife, put in the presentation only the example and not the solution. Because it makes no sense, the solution always to present here with a, it's better in this form, that you can think what I do.
The solution is standing in the paper.
The solution is standing in the paper. We have to look at the paper. I don't know which page.
On page...
I think that's a very...
30 page.
I think it's a very... It's very good to make such a book. It's not so big that... I have a big book. I think Mr. Tim also...
Page 30.
Page 30. So we have... I don't want to calculate here with members, yeah. But if you look here, 5 meters long, the distance of the 6 centimeters is 6 centimeters. Very small compared to 5 meters. Yes, and therefore we have to get. Now I am looking for the formulas. The formulas are here. No, the left and the right one. I think we will almost get the same with both methods.
Yeah.
And if you see on page 30, it's not the same. I tell my students, it's not the same. What's the reason? But the reason is we will get, what happens here? The reactance X of this loop is different and yes, that's different.
Yes.
My students will say, somebody, they're stupid. Why different? It's wrong. But it's wrong. And the students do not know what is significant. Significant Stelle, was heißt Stelle?
Stelle?
Ja, signifikante Stelle.
Points. Oh, yeah.
They measure U 10 volts, E 3 amperes, and they calculate R as
Yeah.
I say,
6 Stellen in dem Komma.
yeah. If they make a report in the laboratory, they have to write it down, and then I get this. And then I say, that is 10%, and then you give me this. No. And the same is here. The same is here. That's almost the same. It's a very small amount. Such your results which the program calculates is 1% correct. 1 to 5% maybe the error, because you don't have you don't know how exactly is the diameter, how exactly long is it, and so in this case it's enough to use the right formula. But if you use the correct formula, you have no work, but you get the same result. But sometimes here is used the complete formula or the approximation formula. I have written down. Okay. So that was the first calculation of one loop with a new method, with a GMR method.
Are there any questions from you? Well, this is a very important step of this day. You are able to calculate simple systems. Yeah. This is the first step going over to the program, yes?
So, then we can go to the next step.
Sind die A und B parallel geschaltet?
C, yes.
Und CD? Sind die parallel geschaltet?
Ja,
Also soll derselbe Strom drauf, der halbe Gesamtstrom drauf fließen.
ja,
Da muss man dazu sagen. Nicht?
ja.
Okay.
Aber das ist ja immer so.
Ja.
But I have forgotten something. Exercise, and there's an exercise for you, but if you want to calculate this, you can do it now. But if you say, I have understood all things, we can make the next step with the next example.
Wollen wir wieder Pause machen?
Yeah,
Erste Pause, ja?
yeah, wirklich so.
Okay. Now we make a little coffee or water break for 20 minutes, up to 3 o'clock. Okay?
Okay.
Kommen Sie mit Ihrem Zeitplan ganz gut zurecht, ja?
Ich habe eher zu wenig, ich habe eher zu
viel Zeit.
zu viel Zeit, dass wir nicht fertig, dass wir morgen gucken müssen, was wir machen müssen.
Ja.
Aber hier kommt dann natürlich noch ein
I also have a question. I'm not here tomorrow. I will take it over on Monday, Tuesday, Wednesday,
Yeah.
on midday.
Yeah.
Okay.
And